All right, today we're going to dive into a really powerful idea called differential privacy. It's basically a way for us to find amazing, useful insights from huge data sets, but, and this is the important part, while making sure the privacy of every single person in that data is guaranteed. So let's see how it works.
This phrase right here, it just nails it. Share insights, not identities. This is the core promise, the whole point of differential privacy. It's all about separating those valuable big picture patterns from the specific personal details of any one individual.
So, this brings us to a huge challenge in our world of big data. Think about a hospital that wants to share data about patient recovery times to help medical research. How can they possibly do that? Find the useful trends without accidentally leaking sensitive health information about a specific patient? It's a massive dilemma. And the answer to this problem isn't just a company policy or a promise to be careful. No, it's a formal, technical solution. Differential privacy gives you a mathematical guarantee of privacy. That means its protection is built on provable stats, not just good intentions.
Okay, so how does it actually work? Well, it all boils down to this beautifully simple concept that I like to call the one-person rule. This is the absolute heart of differential privacy, and it's actually pretty intuitive once you see it. Here's the core logic right here. The goal is super simple. If an analyst runs a query on a data set, the result they get back should look almost exactly the same whether your personal data is in it or not. Your presence or your absence shouldn't really change the final result in any meaningful way. And this just illustrates the point perfectly. Take a look here. With user X in the dataset, the average age is 34.1. Now, take them out, and it's 34.0. For someone looking at these results, it's basically impossible to tell if user X was even part of the group. So, back to our hospital example, a researcher could learn the average recovery time is 10 days, but they could never, ever know if your specific recovery was 5 days or 15 days. Your privacy is totally protected.
Now, I know this sounds a little bit like magic, right? But it's not. The way this is done is by injecting a tiny, very precisely measured amount of mathematical noise into the results. It's just enough random fuzz to hide any one person's contribution while still keeping the overall trend crystal clear. So, how do we control that noise? How much is too much or not enough? This brings us to the control mechanism, the way data teams manage this whole process. And it all revolves around a concept called epsilon. So what exactly is epsilon? Well, the best way to think of it is as your privacy budget. It's a number that measures how much potential privacy is spent or lost every single time a query is run on the data. And just like a real budget, it's a limited resource you have to manage very, very carefully.
I love this analogy. The easiest way to picture epsilon is as a dial. By turning this dial up or down, you're directly controlling that fundamental trade-off between protecting people's privacy and getting accurate, useful data.
And this chart breaks it down perfectly. A low epsilon value means you're cranking the privacy dial way up. The system has to add more noise to protect individuals, which means you get fantastic privacy, but your data is gonna be a little less precise. On the flip side, a high epsilon means you're dialing the privacy down. Less noise is needed, so you get more accurate data, but with a weaker privacy shield. It's a direct trade-off. No way around it.
Okay, so that's the theory, but where is this stuff actually being used in the real world? Let's take a look at some of the common applications and, just as important, the limits you really need to be aware of. You'll find differential privacy popping up in all kinds of fields where you need to see the forest without seeing the individual trees. Stuff like large-scale analytics, telemetry that companies use to improve their products, sharing stats for public research, and even training machine learning models on really sensitive data. Now, this brings us to a super critical limitation. That privacy budget, your epsilon, it's not infinite. You've got a set amount for any given data set, and every single query you run spends a little piece of it.
So this leads to a pretty obvious question, right? What happens if an analyst just keeps hammering the same data set with questions over and over? Can they eventually just chip away at the noise and figure out individual information?
And the answer is a big, fat no, because the budget system is designed to prevent exactly that. As you can see here, each query spends a little bit of the budget. After the first query, maybe you have 90% left. After the second, 80%. Eventually, that budget runs out, and the system just says, nope, no more questions. This is what stops those slow, repeated information leaks over time. So when you put this all together, what we really have here is the ultimate balancing act. It's this constant dance between getting useful data and protecting privacy and finding that perfect sweet spot. The big takeaway here is this. Differential privacy gives you a really solid framework to protect the people in your data, while still letting you see those powerful, big picture trends that drive new discoveries and better decisions. Ultimately, success with this whole approach comes down to one thing: making a really deliberate, thoughtful choice about that epsilon value. It's got to be a strategic decision that perfectly fits the needs of your project and, of course, the sensitivity of the data you're working with. And that leaves us with one final big thought to chew on. We all know our data holds the keys to solving some of the world's biggest problems. The real question for all of us is, how much privacy are we willing to trade to unlock it? It's a question that leaders and all of us are going to be grappling with for years to come.